The purpose of today's lesson is to give you guys a really full, rich understanding of metabolism and the whole bioenergetic continuum, which is, the moving from, food down into like glucose into like ATP, and the various ways that we use that, how we can write programs to effectively like utilize different parts of the bioenergetic continuum. So after this presentation, we want you to be able to understand like how we produce energy. So we're going to look at glycolysis, the electron transport chain, the Krebs cycle. We want to differentiate between what is aerobic versus anaerobic, right? Anaerobic without oxygen, aerobic with oxygen. Distinguish which energy pathways predominate for various intensities during exercise. Such a fancy way of saying like we also want to analyze like how the different energy systems are used for different intensities with our clients, right? So that is another one that we're going to be looking at. We definitely want to look at how carbohydrates, fats, and proteins are used for fuel, the different energies that are going to be used during versus like steady state cardio versus like, exhaustive, super high intensity cardio. That's kind of the same thing as like looking at which one is sort of determined by like the energy system, and then we want to look at like the basic training adaptations when it comes to like energy production. So like when your body gets better at certain parts of this, what are those adaptations going to look like? So everything, I would say everything in this PowerPoint, all of this stuff that's in your notes over here is definitely like relevant to passing your actual exam. So this, like I said, like, Sochi gives you guys a lot of extra information, stuff that isn't necessarily always going to be like directly on your test, but it helps you have a deeper understanding of the stuff that is. Everything in this PowerPoint is directly on your test. This is all like very key vocabulary, which is why, again, everybody wants to read chapter 4 this weekend or read chapter 4, hopefully later today. Looking at the first thing, our first key definition here, which is makes a great test question. They want you to know this definition. What is bioenergetics, right? Bioenergetics is the study of how energy is transformed through biochemical reactions. So when we're talking about like taking in proteins, fats, and carbs and spitting out an energy that we are able to like utilize in this form of ATP, right? So like how we take in food, how we generate ATP, then we get to use that ATP to generate, to do work and stuff. But that is bioenergetics. It's the study of how those different pieces come together in these like chemical reactions, so that we can do all of our work. We are also going to look at metabolism. This is a definition you guys have seen, but that is all chemical reactions that are taking place inside the body. If you break an ATP molecule, that's part of metabolism. If you generate an ATP molecule, that's part of metabolism. You take glucose and you break it, or if you take carbohydrate and you break it down into glucose, that's part of metabolism. Any chemical reaction, there's a chemical reaction, whether it's hydrolysis or dehydration synthesis, it's part of metabolism. But there is a special term that we are going to use, which is exercise metabolism. And the exercise metabolism is probably the one that most people actually think about when they think of metabolism. So like most people, they're like, you ask them what their metabolism is, they say like, oh, no, it's about how many calories you burn every day, right? It's a pretty common answer. That's a little bit closer to the idea of like what an exercise metabolism is. So your exercise metabolism is the examination of bioenergetics, how energy is transformed through various chemical means, as it relates to the unique physiologic situations that we are putting our body in while we are exercising. So exercise metabolism is literally what how your metabolism reacts when you are exercising, right? Very different than just regular old metabolism, right? Like your red blood cell production, right, is part of your regular metabolism. But, producing red blood cells isn't part of exercise, although, it is sort of a byproduct sometimes. So looking at this, if we're going to talk about like producing energy, we have to talk about like where we're getting that energy from. And we're going to get our energy from our nutrient substrates, which is the small versions of nutrients that we consume every day, right? Carbohydrate substrate is going to be glucose. Fats substrates are going to be lipids, and protein substrates are going to be the amino acids, right? So looking at proteins, fats, and carbs, and understanding like how these work and how they are broken down to produce like cellular activity. So carbohydrates are probably your body's favorite. They're used directly for metabolism, right? So your body loves carbohydrates as an energy source because glucose can be broken down into energy very, very, very quickly. So because there's really no like, waiting around for glucose metabolism to take place, it's your body's preferred source. Your nervous system, for instance, is pretty much on an exclusive glucose diet for the most part. So your body loves this so much that it actually has the ability to store carbohydrates within the body. We're going to call that glycogen, right? So your body will store carbohydrates in the form of glycogen. So if we look at like carbohydrate starches here, there's a lot of different types of starches out there, but generally starches kind of look something like this, right? They're these big, long, complicated chains of carbohydrates. So, you've seen this plenty of times. If you've ever had, bread or rice or like, beans, like the carbohydrates that are making that just complicated, all of this, like all these starches coming together, like, all these glucose molecules coming together. When there's hundreds or thousands of them, we call it a starch, right? Now your body is able to store carbohydrates in a starch form that we call glycogen, right? And so you can actually even see, I clicked the wrong freaking thing and that took me away. Glycogen looks just a little bit different, right? You can see like starches are fairly straight, but then like glycogen is just like a slightly more organized version of like starches, right? You can see this a little bit, kind of has this interesting shape. And then this one is like a little bit more organized, a little bit more complicated. And what's kind of cool about glycogen, because of this shape right here, it doesn't actually form together very well. So it doesn't make a solid. And the way that like a potato, which is a pretty solid object, glycogen doesn't necessarily look like that. Glycogen is actually kind of a liquid inside that we store inside of our muscles, and we store it inside of our liver. So those are the two places that we're going to store onto glycogen. And the reason we do that is because if I need a glucose molecule, I can come over here and just peel this one right off the end, and bam, I've got some glucose to do some energy. If I need another one, great, bam, break it off, right? This is why your muscles will store onto glycogen. And if you've ever like seen somebody who runs like if you get, the Ironman triathlon, right? So the Ironman triathlon is arguably one of the hardest events in the world. And it is an absolutely wild, experience. It is what, 70.3 miles or something, but it is the Ironman triathlon in terms of like its distance. What is it? It is a 2.4 mile swim, followed by a 112 mile bike ride, followed by a 26.2 mile run. So that is, and it's all in one day. So that's about like, probably 17 hours worth of exercising in one day. Like it is a literal all day event that is meant to be absolutely insane and crazy. Here's the thing, because this event is so tough, people can die doing it. They'll push themselves to heat exhaustion. Not very good, right? So it's interesting, when you're running these Ironmen, they will actually have tents set up and they will weigh your body. And if you drop too much body weight from like checkpoint A to checkpoint B, they will pull you out of the race. And you might be asking yourself, well, where the heck is that body weight coming from? Well, some of it is water, right? Some of the water is being evaporated because your temperature is going up and you're producing lots of energy to be able to run through this race. but a lot of it is also your glycogen. And if you tap through your glycogen too quickly, what will happen is your body will have to find carbohydrates, because that's your body's preferred source of metabolism. It'll have to find carbohydrates from somewhere else. And so, well, one of the things we're about to talk about is how proteins or amino acids can be broken down into carbohydrates very quickly. So your body will actually take protein and convert it to carbohydrates in order to make up for the lack of carbohydrates. That may not sound so bad, except that that's how you catabolize your muscles. That's how you eat away at your muscles. So we can call it cannibalize, because your body's eating itself. And if that happens, there's some byproducts that are left over in the form of like nitrogen. That nitrogen's like running through your bloodstream now, gets filtered out by your kidneys, and your kidneys can shut down mid-race. So that's one of the reasons why they keep a very strict eye on your body weight during these races. They want to make sure that you're not losing glycogen too quickly. And for the record, you guys have probably seen something that looks really similar to glycogen if you've ever boiled a pot of potatoes. If you've ever like been making potatoes, or even like in rice, sometimes you'll see it. Like if you didn't wash it very well, you'll see that like scum that kind of comes to the top of the pot, like as you're boiling it, there's all that like scummy material. That's actually kind of what glycogen looks like inside of your muscles and inside of your liver. It's this kind of wet, soupy starch. So that's glycogen, right? We definitely want to make sure we have plenty of that if we are going to do physical activity. This is why carbohydrates are so important to get after your workout. And that's what's kind of funny, you know, like you'll hear trainers that don't study nutrition very much. They'll often say, well, you need to get some carbohydrates before your workout so you have energy to work out. And then you need to get some protein after your workout so you can like repair any damage you created. I actually don't dislike that advice, but I think it's very incomplete. You want to have a blend of carbs and protein before. You get a little bit of protein. Whoa. Excuse me. You get a little protein in your diet beforehand, which will ensure that like if you have some amino acids running through your body, cellular repair can start like right away. And then you want to make sure you have plenty of carbohydrates because yeah, it does give you energy. And then after your workout, you want to get plenty of protein to repair any cellular damage that you created, but you also want to get plenty of carbohydrates. Now, the reason you want to get carbohydrates isn't so much because it's going to build massive amounts of muscle or anything like that. It's because hopefully you're going to work out again tomorrow. And you just broke through all of your glycogen stores. You just used them all up and burnt it all up for energy, right? So make sure that you restore those darn things before you go try to work out again. Because then your workout, you know, if you're exhausted, you won't be able to work out very hard. And if you don't work out very hard, your body has no reason to adapt. So we definitely want to have a blend there. So carbohydrates are definitely your body's favorite source of energy. Another source of energy that we've got is fats. Fats can actually be used directly for metabolism, which is kind of nice. You know, this is where basically your body is going to break down fats into triglycerides, and then triglycerides are basically going to skip glycolysis and go right into the Krebs cycle. So if we look at like how fats are going to be used for energy production, they go through this process called beta oxidation. And beta oxidation basically converts fatty acids or triglycerides. It will kind of break them down and turn them into acetyl-CoA. Okay. And acetyl-CoA is what starts off the Krebs cycle. Like if we look at the Krebs cycle here, right? Remember, we go back through talking about like energy production, which we're going to do again in just a moment. I guess this won't work. When we look at like going through all of metabolism, it starts with glycolysis. Glycolysis gives us ATP and it gives us pyruvates. Pyruvates ferment into lactic acid. Lactic acid gets converted into acetyl-CoA, and that's what starts the Krebs cycle. Okay, so the Krebs cycle begins right here. Now, if you had a molecule of fat, you can skip glycolysis entirely. And with enough oxygen, this is what we call beta oxidation, and oxygen levels that are present enough, your body can basically jump right to this step right here, generate some acetyl-CoA, and go through the Krebs cycle. This is basically what keto diets are entirely like based on. Has anybody in here ever tried keto? Do I have any keto people in here? So I'm asking, even if you just goofed around with it for a little bit. Thomas, Bay, Cody, anybody?
No.
Never? So the ketogenic diet, right, is not necessarily, like the idea here is that your body is running on ketone bodies, right? And those ketone bodies are the mid step that eventually becomes that acetyl-CoA. So basically your body will convert fat into ketone bodies, which will then convert that into acetyl-CoA, which will then go through the Krebs cycle. And then we can just, once we're through the Krebs cycle, we can go into the electron transport chain. And that's cool and all. There are various times where, you'll actually be going through ketosis throughout the day, which is the state in which there are excessive ketone bodies running throughout your body, right? So ketosis is where you have a lot of ketone bodies built up. And so your body is going to start using those for energy. And that's really good for long, sustained, low intensity energy, but it's not so good for high intensity energy production, which is where glucose really comes in. Glucose kind of shines when it comes to like producing lots of energy very, very, very quickly. Ketosis is pretty good at like the Krebs cycle, but that's a very kind of slow process. It's a very aerobic process. So it can be very good for like energy production in the long term. But if you are an athlete and you are trying to like lift at maximal intensity, it can be a pretty challenging fuel source for you to use, because if you're in the middle of like glycolysis, you just won't have the carbohydrate production to be able to do it because you're on a basically 0 carb diet. I think they're allowed like 25, 30 grams of carbs a day or something. Very, 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 very low. So fats can also be used directly for metabolism. So those are the two preferred fuel sources, right? Carbohydrates and fats. And they work in very different ways, right? If we look at like carbohydrates versus fats ratio. Intensity ratio is actually what I want. Yeah, close. Respiratory exchange ratio. There we go. Okay. So take a look right here at this chart. Remember, we talked about how the respiratory exchange ratio, or the respiratory quotient, is the amount of oxygen that is being consumed versus the amount of CO2 that is being exhaled, right? So if you bring in 100 units of oxygen and 70 units of that oxygen get burnt up as energy, there's only a 30 remaining. That means that your RER is about 70%, okay? And then as your intensity starts to climb, it gets up to 100%, where it's like, okay, well, every unit of oxygen I bring in is all being consumed directly. I'm using all of it, right? And so the only thing you're exhaling is pure CO2 at that point. You're at a respiratory exchange ratio of 1.0 or 100%, right? That's where, we took everybody yesterday during our in-person thing. We brought everybody up above their anaerobic threshold, the moment where it's official, they are burning 100% of their energy from carbohydrates. Or 100% of they're using 100% of their oxygen. So based on where you fall on the respiratory exchange ratio, somewhere between 70% and 100% oxygen utilization or oxygen consumption, you have a blend of using fats as your fuel source for activity or carbohydrates as your fuel source for activity. So if we think of like a respiratory exchange ratio of 70% or 0.7, as you are doing as little work as possible, like you are laying in bed asleep, right? The only thing your body is doing is keeping itself alive. Well, that's 70% of the oxygen you bring in is being consumed, but the remaining 30% just isn't even getting used. So you just exhale it. Well, when you're like that, when your intensity is at its lowest, you are burning 100% of your energy from fat. Fat, which again goes straight into the Krebs cycle, it skips the glycolysis, is really good at energy production because there's a lot of energy trapped within fat, but it's kind of slow, right? It produces plenty of energy, but very slowly. So it's almost like, it gives like a big burst and then like waits a little while and it's kind of slow, and like gives a big burst and then kind of waits a while and it's a little slow, right? That's kind of how your aerobic metabolism works. It gives like a big energy release and it's kind of slow in how it does it. Versus glycolysis, which produces a very little amount of energy. You only get like 2 ATP, right? But it produces it rapidly. It's like a lot of little tiny explosions, right? So if you imagine like, propelling a car with like a rocket, that eventually like kind of burns up and then it, takes a little while. You have to, reload it and attach like another rocket to it, right? Like, that would very much be like running on like fats, right? It'd be like, okay, I got lots of energy, and then and it runs out of fuel, and then it kind of slows down, and then you reattach another one, you get to go again. Versus like carbohydrates, which is like lots of little tiny explosions. That's like literally a car running on gasoline, right? And the pistons are just firing like crazy because it's just like a series of, lots of little tiny explosions. Not a big enough explosion to, blow up your car, but a big enough explosion to propel you a couple inches forward, and then another one, and that's how we, literally drive. So at least I think I know jack about cars. But that's sort of what we're looking at. So we're always in a blend of somewhere between 70 and 100%, which means we're always in a blend of using a combination of fats or carbohydrates for fuel source. If you are 100% at rest, you are burning all of your energy from fat because it's low intensity. And if you are at 100% intensity, you're working as hard as you can, you are burning all of your energy from carbohydrates. So we are in a blend of this all the time. Like right now, you guys are probably at like what, 7.2, 7.4, if you're sitting down listening to me right now, right? You're just above waking. So most of the energy that you are supplying your body with right now is coming from fats. Now, if I made everybody start doing burpees right now, and you start to like get to a place where you're completely out of breath, right? It's like, we're going to do maximum intensity burpees. I want you jumping as high as you can, do it as fast as you can, high and as fast as you can. And you're getting to this point where you're like, and you feel like you can't catch your breath anymore because you're above your anaerobic threshold. You can't bring any more oxygen. You can't consume any more oxygen because you're just tapped out, right? Well, if you get to that point, 100% of your energy is coming from carbohydrates, right? This is our anaerobic metabolism, and this is our aerobic metabolism, right? So we're seeing a little bit of a blend there. So if you've ever wondered where the fat burning zone is, which you'll see on treadmills, right? You'll see like the fat burning zone in a treadmill. You always see it on like the pictures, right? You look at like a treadmill, it'll have this thing here where it's like, if you're this age, so if you're 20, 30, 40, 50, whatever, right? If you're that age, then you want your heart rate to be 140 to be in the moderate zone. But if you want to be in the fat burning zone, you got to be only at 130. It'll tell you your heart rate to be a little bit lower. And so people will see that fat burning zone, they'll see it on a treadmill and they'll go, oh man, like that's what I'm here for. I'm here at the gym so that I can burn fat, right? And so what they'll do is they'll focus entirely on that low intensity stuff. But the problem with low intensity is, number one, it doesn't trigger your body to like experience change. So that's not very great. And it doesn't burn that very many calories. So how the heck do we get to burn like lots of calories? And then how do we ensure that those calories are coming from fat? Well, that's where interval training comes in. And so we'll come back to this concept at the very end of the lesson today. We're going to come right back to this respiratory exchange ratio one more time when we apply it to everything that we're talking about. So, but for now, carbohydrates and fats are our two favorite fuel sources. Now, there is a third fuel source, obviously. We've got carbohydrates in foods, we got proteins in foods, or we got fats in foods. We also have proteins in foods, right? So protein can be used for energy production. There are obviously calories in protein, about 4 calories in every gram of protein. But here's the thing. If you look at a carbohydrate versus a fat, right? Let's see, lipid chemical structure. If you take a look right here, this is what fat looks like, okay? No. That's definitely not a fat, actually. There we go. So here's a triglyceride, right? This is what it looks like. It's got oxygen in it. It's got carbon in it, which you can see is the skeleton here in the middle. And it's got lots and lots and lots of hydrogen, right? Which, by the way, hydrogen, remember, that's what goes through the electron transport chain. Again, this is why fats are so good for aerobic energy production, low intensity, right? So oxygen, carbon, and hydrogen. And then glucose, same 3 ingredients. If you look at glucose here, carbon, hydrogen, and oxygen, right? So carbon, hydrogen, and oxygen, carbon, hydrogen, oxygen. They're just shaped differently, you know? That's the only difference between carbohydrates and fats is, you know, they're the same 3 ingredients. They're just shaped a little bit differently. But then we have amino acids, okay? And amino acids, they look very different. Amino acids actually have a 4th ingredient. They've got a little bit of nitrogen, okay? And then they got this little carboxyl group. Don't worry about that, but that's carbon, oxygen, and hydrogen again. But like, see this little N right here, and then see this little R right here. So there's no R on the periodic table. This R would actually kind of open up, and it would look different depending on which amino acid it is. That's what we call a side chain, or an R group, depending on who you're talking to. They mean the same thing. But the side chain is basically where there'll be kind of a unique shape to that nitrogen. So they'll all look a little bit different, right? You can see like all these amino acids all look just slightly different from one another. This right here is sort of a fake amino acid. This is just meant to be a generic example version. But again, what I'm trying to show you right now is just that we see hydrogen, we see carbon, we see oxygen. Those are the same ingredients that we saw in glucose. And it's the same ingredients that we saw in like fats here. But then we got this little bit of nitrogen. Okay, so if your body wants to use protein as energy, what it can do is it can take this amino acid and it can strip the nitrogen away. It can just pull the nitrogen skeleton right out of the body of the amino acid. And it will kind of change its shape, and then it will turn it into a molecule of glucose. So it will literally take an amino acid and just turn it into carbohydrates. This is one of the things that knocks people out of the ketogenic diet all the time without them realizing it. A lot of people think like keto diets are nothing but like lots and lots of protein and fat, but it's actually a moderate amount of protein, like a normal amount of protein, and lots of fat and no carbs. But what happens is if you are on the keto and you eat like way too much protein, remember your body's favorite fuel source is glucose. So if your body goes, well, I want glucose, and we got all this extra protein laying around, it will turn the proteins, it will turn the amino acids into glucose molecules. And then it's just going to go through the normal glucose metabolism. It's going to go right through glycolysis into the Krebs cycle, into the electron transport chain. This is where you catabolize, or cannibalize, as I like to say, your muscle if you do too much physical activity and don't give yourself enough calories, right? You know, you see people who will exercise all the time and they lose massive amounts of muscle mass. Well, your body is losing that muscle mass in response to the stress that you're putting it through. Your body's going, wow, we burn a lot of calories every single day. And so then what it chooses to do is it's like, I'm going to get some of those calories from protein, because proteins in your body, your muscle cells in particular, burn a lot of energy. And if you're having energy problems, you're not giving yourself enough fuel to supply yourself with enough energy, you're having like these problems keeping up, your body will go, all right, well, I'll make the body less muscular. I'll make it less strong. and that'll mean we burn less calories. Kill two birds with one stone. I get the energy production that I want, and we burn less energy overall. It's like if you're, in a rowboat that was sinking, you would get rid of the heaviest item first, right? If you're like trying to like bail stuff out, you're like, it's like, okay, well, we've got some rations of food over there. We got a flare gun over there. Oh, and then there's a popcorn machine. Throw the popcorn machine overboard. That thing weighs like 100 pounds. You're going to get rid of the thing that burns the most energy. That's your body getting rid of protein. This is why we want to make sure we have adequate protein in our diet to tell our body, no. We got plenty of energy. We got plenty of, we got plenty of calories. We got plenty of protein in our diet. Like, keep the muscle, right? That's us trying to signal that to happen. So how does your body convert proteins into carbohydrates? Well, it does it through a process called gluconeogenesis. Your body is generating glucose from amino acids, right? So it converts, proteins are converted into glucose through gluconeogenesis, and then that glucose is used for regular old metabolism, right? So gluconeogenesis is a term, I know it's in I think it's in your homework 3. This is a term that will definitely come up many times because it's basically something we are trying to avoid at all costs. So NASM's going to ask you about this for sure. But it is the formation of glucose from non-carbohydrate sources like amino acids. So try to avoid gluconeogenesis. Give yourself enough carbohydrates to ensure that your body can maintain its muscle mass rather than turning your muscle mass into sugar to be used for energy. When I put it that way, it's like, okay, yeah, that sounds like a great deal. And there's another reason why we don't want to go on a starvation diet. How are we doing so far, guys? Thomas, Bay, Cody, how you guys feeling?
Pretty good.
Cool. Hopefully some of these concepts are actually starting to like all kind of come together. You probably noticed that like some of these are kind of linked to things that we've already talked a little bit about. By the way, also speaking about like losing muscle mass, one of the things we're going to get into nutrition in our next course. So starting in like 2 weeks, I think. Starting a week from this Tuesday. So, the next Tuesday. We'll start going into nutrition. And one of the things that we're going to talk about in nutrition is ensuring like that you have enough calories. How much weight should you lose per week? It's hard. That's a hard question to answer sometimes. And researchers have kind of looked at it, and they've found that the perfect rate for weight loss is about 0.7% of your overall body weight per week. Any more aggressive than that, and they find that like you lose massive amounts of muscle mass because your body goes into starvation mode and freaks out. But 0.7% is about the maximum amount of fat, or about maximum amount of like weight you can lose per week while maintaining as much muscle mass, getting the most bang for your buck. So if that was me, for instance, right? God dang it, computer. Times 0.007, I'd want to lose about 1.26 pounds per week at the very most. And that doesn't sound like very much, but then again, like that's what happens. If I weighed, 300 pounds, I could lose 2.1 pounds per week. That'd be a lot faster, right? So it's a little bit different. Everybody's a little different. We'll talk about that in nutrition, which will be kind of fun. Okay, so let's look at ATP here again. So adenosine triphosphate, or ATP, this is the primary source of energy for immediate cellular metabolism, right? ATP is basically where we are, the whole purpose of metabolism is to generate as much ATP as possible. And having ATP is what allows us to do literally everything we do, right? When you have a thought, that takes a little bit of ATP. It burns just a little bit of energy because like you have to like flush sodium and potassium ions. That means that you got to open pumps and squeeze channels and move sodium ions and potassium ions to different places. That takes energy, right? When you want to move a muscle, that takes a lot of energy, right? When you want to process food, when you want to create an enzyme, all of this takes ATP, right? So the energy to perform work is trapped within ATP. So we store energy within the chemical bonds of an ATP molecule. And so when we look at ATP, it looks kind of like this, right? You can see it actually, whoops, it's a molecule of what's called adenosine, which is a little protein over here. Again, you can see the nitrogen that's making it a protein. And then it's attached to a little sugar called ribose. So that's adenine plus ribose. There's where we have our adenosine molecule right here. Ribose is a sugar. It's the same one that's actually found in your DNA there. And then you'll see a little bit of oxygen, a little bit of hydrogen. And then we see these little P's right here. And that's phosphorus. And that's why these are called phosphates. So you got 3 phosphates there. I like that picture, but I'm going to choose a slightly different looking one. So now you can kind of see it looks something kind of like this. So these are our 3 phosphates. And the energy that we want to extract is kept right in here. There's a ton of energy trapped between this bond and this bond, the 2nd and 3rd phosphate. So if we kick off that 3rd phosphate, we break that chemical bond, lots of energy gets released, right? Just like, you know, let's see what happens if I Google split an atom. If I Google this, you can see like splitting an atom. Yeah, there we go. Big explosion. The smaller something is when you split it, the more energy gets released, right? That's how we have like nuclear power plants. That's how we have atomic explosions as well, which we're trying to avoid. Well, we're not doing that on a huge scale like that. We're not trying to release that much energy. I wonder how many calories worth of energy would be. I wonder if this is Googleable. Somebody's done this math. How many calories are in an atomic bomb? Someone has Googled this before. Oh, this is looking up like something called atom bombs, which is like a food. It would be, I'm sure it would be billions, literally billions. There's the formula. Yeah, it would be a lot. It would be a whole lot. Anyway, so billions and billions and billions of calories. So then we've got, we're doing a much smaller version of this in terms of ATP, but that's how we are, you know, capturing that energy. We're releasing this chemical bond. So the body breaks the phosphate. That releases the energy that's trapped within, and the body uses that energy to do work. And afterwards, we're left with the wreckage of an ATP molecule, which we are going to call adenosine diphosphate, or ADP. So if you were to like be left with just 2 phosphates, we'd call it diphosphate, right? Which you can see they're kind of labeling out in this picture. It's like adenosine diphosphate is like all of this. And then if you were left with just like, you know, you could actually still break ADP down and get some energy out of that, which is kind of cool, you know, but there's definitely not as much energy trapped between the 1st and the 2nd bond. Not as much energy at all. But you can still get it. And then you'd be left with AMP, which is adenosine monophosphate, you know, 1 singular phosphate and then the adenosine here. And that actually has been shown to interrupt muscular growth. AMP is actually something we are trying to avoid making if our goal is to experience like muscle growth, which is why, again, theoretically, this is one of the reasons why we see the difference between like a sprinter versus a marathoner, right? Sprinters are, you know, creating lots of energy for a very short period of time. Marathoners are creating, you know, chances are this person ran out of ATP, so they started converting it to ADP. And then that actually has been shown to interrupt muscular growth. So again, one more reason to get enough calories in your freaking diet. And also one more reason to not exercise 8 hours a day. I know we all love exercise, but like it should be brief and intense, you know? So those are ATP molecules. Let's take a look at producing this, right? So until now, we've really been talking kind of heavy about glycolysis and your oxidative metabolism, right? These are your energy systems, right? But there is a 3rd one that we haven't been talking too much about, which is called your ATP Pc system, or the adenosine triphosphate phosphocreatine system. Now, this system actually predates glycolysis. This will actually take place before you get to glycolysis. So glycolysis comes before your oxidative metabolism. The ATP Pc system comes before glycolysis. And this is, if glycolysis was our high intensity energy system and the oxidative was our low intensity, you can think of the ATP Pc system as the super ultra crazy intense intensity energy system. So this only lasts about 6 to 10 seconds if you are awesome at it. If you're somebody like me, it might even last even shorter than that. But this provides energy for short duration, ultra short, high intensity, ultra high intensity energy by replenishing ATP very, very rapidly. So the ATP Pc system actually doesn't generate any ATP directly. Instead, what you'll see is we've got a molecule of ATP over here, right? There's our adenosine and 3 phosphates. We kick off that phosphate. Well, creatine, which is a thing that your body generates naturally, has its own little phosphate here. And so what it'll do is creatine will donate its 3rd phosphate to reattach to that adenosine molecule, and you'll be left with ATP. I always like to think of it as like, imagine if you had an ATP molecule, you broke the phosphate off, and then you just reattached it right away. Broke it, reattached, broke it, reattached, broke it, reattached, just over and over and over and over and over again. That creates a ton of energy really, really, really quickly. So when we think about the ATP Pc system, like I said, you only can stay here for about 6 to 10 seconds. This is your maximal intensity style of lifting. When you think about like, Usain Bolt, right? And actually one of his records was just broken. But his record in the 100-meter dash was like what, 9.58 seconds, right? So he is in the ATP Pc system for most of his event, right? He is entirely focused on training within this energy system versus a marathoner who's got to run for 2 hours. They're primarily focused on the oxidative system, right? And then there's a 400-meter dash athlete. 400-meter dash, that's going to take probably 45 seconds. Well, they're spending most of their time training for the ATP Pc system so they can get up to speed really quickly. And then they spend most of their event in glycolysis, which is the medium intensity, right? So generally when we're lifting weights, we spend most of our time in glycolysis. But if you do ultra high repetitions, you'd get into your oxidative metabolism. And if you did ultra low repetitions, maximum intensity, super hard lifts, you'd be training for your ATP Pc system. So it's almost like we've got power lifters here, we've got bodybuilders here, and we've got cardio athletes here, if we're being very overly simplistic. So that's the ATP Pc system. We'll take a look at it a little bit better in just a second. Then we've also got glycolysis. Glycolysis is going to provide energy through the breakdown of glucose, right, to produce ATP. This is moderate intensity, moderate duration work, right? Every 1 molecule of glucose, you get 2 molecules of ATP, and it produces them really rapidly, right? Again, not as rapidly as the ATP Pc system, but definitely more rapidly than oxidative. It's in the middle, right? And this provides duration for, or provides energy for your moderate intensity. So like still pretty freaking heavy, but not as heavy as this stuff over here. Moderate duration. So still a relatively long period of time, like up to 50 seconds. That's 5 times longer than this, but definitely not as long as this, which can last, I don't know, 100 years, like your oxidative metabolism is what's been running your heart since before you were born, who's the oldest living person? 122 years old, that is very oxidative. I'd say that's greater than 2 minutes. So glycolysis, right? Medium intensity. Generally, we think of this as lasting about 30 seconds in general, but if you're pretty good at it, maybe 30 to 50 seconds. If you're really good at it, maybe even longer, depending on how incredibly good at it you actually are. So this is associated with moderate intensity work. If you think about doing like 6 to 12 repetitions, you are definitely staying within glycolysis, right? Think about 6 reps and it takes you maybe 4 seconds per repetition because you're moving at a medium tempo, like 1, 2, 1, 2, right? Then that would be 6 times 4. You'd have about 24 seconds. You are literally right in the middle here. And then if you were to take it up to 12 repetitions, that would be, 12 times 4. That'd be 48 seconds. So you're literally spending all of your time in glycolysis if that is how you are lifting. And that's why hypertrophy, which is the middle of the OPT model, and mostly focused on muscular growth, well, hypertrophy is relying on glycolysis. Glycolysis produces lots of lactic acid as a byproduct. Lactic acid creates cellular damage. Cellular damage creates inflammation. Inflammation creates muscle growth and size. Therefore, hypertrophy is in the middle of the OPT model because it's not super high intensity and it's not low intensity. It's not short duration. It's not long duration. It's in the middle of everything. And that's why we're looking at that, right? This is why this is associated with muscle growth. And then we've got your oxidative metabolism. Your oxidative metabolism is the most complex because obviously this has, different components to it. And that is going to be using the substrates of your other energy system. So remember the lactic acid that we generated in glycolysis, we're going to burn that lactic acid up, convert it into acetyl-CoA, and then acetyl-CoA will go through the Krebs cycle. That's awesome, right? We recycled the byproduct from glycolysis to generate energy in the Krebs cycle, right? And in the electron transport chain. So if you want to keep that lactic acid around, well, then you should stop exercising. You should rest before your next set. But if you want to, get better at endurance and you want to produce more energy for greater durations, well, then we're going to train in that oxidative metabolism where, we are going to go with a duration of, maybe greater than 2 minutes sometimes, right? So this is definitely the most complex because it's using the byproducts of glycolysis and it's producing energy in 2 ways. You got the Krebs cycle and the electron transport chain. Krebs cycle takes the byproducts from glycolysis, spits out 2 more ATP, and then it makes its own byproducts in the form of NAD and FAD. NAD and FAD go through the electron transport chain. We get 36 molecules of ATP at the end. I think he said 34 in the video earlier. Like I said, these numbers do kind of shift a little bit. So that is a duration of 2 minutes or greater. This is associated with your low intensity, long duration lifts. So if you think about 12 repetitions, again, that was at the very end, right? If that was a 202 tempo, that'd be 48 seconds. It's just at the end of glycolysis, just maybe at the start of oxidative metabolism. And then up to 20 repetitions, which 20 repetitions, 20 times 4, that's going to be 80 seconds. That is very much oxidative. You are out of glycolysis at that point. But here's the thing. NASM takes this even further. They don't make you do 12 to 20 repetitions in stabilization at a 202 tempo. They make you do it at a 421 tempo, which means it takes 7 seconds per rep. 1, 1, 2, 1, 2, 3, 4. 1, 1, 2, 1, 2, 3, 4. 7 seconds per rep. So then what the numbers actually are, 7 times 12, that's a minimum of 84 seconds, very oxidative, or 7 times 20, that's 140 seconds. That's greater than 2 minutes. That's very much oxidative. And trust me, you try to get to the end of a 20 repetition set at a 4-2-1 tempo, guys, it burns like crazy because you are producing lots of lactic acid in the background and you're trying to convert it and you'll start breathing hard like you're doing cardio. So you can start to see the energy systems are kind of flipped upside down on the OPT model, right? We start oxidative, we train that first because that's low intensity and that's going to be safest for our clients. Also, it's going to build us, a good foundation of endurance. Then we lift a little bit heavier where we start to get into glycolysis, and then we lift even heavier and we start to target the ATP Pc system. So it sort of goes in reverse order there. So here's what those durations look like, by the way. I pulled this chart up on the first day of class, but you can see in this side down here, this is representing duration. This side up here is showing you what percentage of the energy system all of the energy is coming from. So when your duration is less than 10 seconds, all of your energy is coming from that phosphagen system, the ATP Pc system, right? That's your immediate energy. And then as soon as you like end up like going past 10 seconds, it's like, it just dies off. And it's like, once you're 30 seconds in, you've got no more creatine left. So you're definitely not using any ATP Pc system at that point. But luckily, glycolysis has had time to start converting sugar into energy. And so you'll end up in glycolysis. And then that'll take, and once you're about 30 seconds in, all of your energy is coming from glycolysis. And then it starts to die off. If you start to get any greater than 2 minutes, you know, your glycolysis starts to kind of fall off the edge there. And then luckily, your aerobic metabolism has slowly been amping up. And once it gets up here, this chart could literally extend into infinity. And that's your long-term aerobic processes, right? So that is energy as it is at work there. So let's go ahead and take a look one more time at these energy systems here, right? So the ATP Pc system, or the phosphagen system, the way it works is you use a phosphocreatine, that's the PC, which will use hydrolysis to break, remember hydrolysis is how we break stuff up, but it'll break off the phosphate from the phosphocreatine and then take that phosphate and attach it to your ADP molecule. That'll reform it. There is a little enzyme present in creatine that's responsible for this chemical reaction. We call that chemical creatine kinase. So you can see you've got ADP and some creatine. Creatine kinase will reform your ATP molecule by taking the phosphate and moving it over here. And then you're left with, you know, some energy, ATP, and a little bit of creatine that's left over. This is why we take creatine as a supplement. And this is one of the only reasons you'll hear me, you know, back creatine as a supplement. Like a lot of people ask me all the time, which supplements really work, you know? And one of them that I will always say works really, really well is creatine. But you also kind of have to look at it. It's like, all right, well, creatine is effective, but what is it effective for? It's really good at making you use the phosphagen system. So if you're training for like 12 to 20 repetitions, or even like 8 to 12 repetitions, is creatine doing anything for you? Not really, because like by the time you're at 8 repetitions, you're mostly dipped through your creatine levels, you know? If you want to use creatine to its most effectiveness, you need to keep your reps low. I'd say anywhere from 1 to 6, maybe 8. And that's where creatine is going to be the most effective. So all forms of exercise will start in the ATP Pc system, but particularly the high intensity ones. So when you think about like Olympic sprinters, power lifters or Olympic weightlifters, gymnasts, right, who are super explosive and fly through the air, you know, use their muscles for a half a second to fling themselves 100 yards, you know, like, maybe an exaggeration. That is very much your phosphagen system, or your ATP Pc system. So high intensity work. Then you got glycolytic system, or glycolysis, right? The glycolytic system is where we are converting glucose into pyruvic acid, or pyruvates. And then those pyruvates eventually become ATP once they ferment a little bit. So 1 molecule of glucose gives us 2 molecules of ATP. It also gives us 2 molecules of NAD. NAD is eventually going to go through the electron transport chain later and get converted into, that will get converted into energy. But that pyruvic acid is converted into lactic acid. And lactic acid gets turned into acetyl-CoA. Acetyl-CoA starts the Krebs cycle. Again, it's a lot of like, We make this, we get a byproduct. That byproduct starts the next system, you know? So actually, I do have a little video here that I want to show you, but I keep this one on my computer. Video presentations. This one.
While ATP is the fuel that supplies the energy for muscles to work, unlike some other types of fuel you might be familiar with, it's not a case of simply filling up the body's tank with ATP and off we go. In fact, the body has 3 different energy systems, and they all work together to enable our muscles to contract and allow us to perform an incredible range of movements. The first 2 energy systems we'll examine are called anaerobic energy systems. That is, they function without oxygen. Firstly, the Atp Pc system. Pc stands for phosphocreatine. Let's look more closely at an ATP molecule. Its molecular diagram looks like this. When the energy from an ATP molecule is released, one of the phosphate groups, consisting of 1 phosphorus atom and 3 oxygens, splits away. The remaining molecule is known as ADP, or adenosine diphosphate. Its molecular diagram looks like this. But when PC, or phosphocreatine, which is also found in muscle cells, reacts with ADP, it donates a phosphate group to the ADP molecule, and an ATP molecule is again formed. When PC gives off its phosphate group, a molecule known as creatine is left. For this reaction to take place, an enzyme called creatine kinase must be present. This series of reactions is the basis of the ATP Pc energy system. ATP synthesizes to ADP and resynthesizes to ATP with the help of Pc molecules and the enzyme. These reactions take place very quickly inside the muscles, and because Pc is stored in the muscles, it is the first energy system used during high-intensity physical activity. The muscles only store about 10 seconds worth of Pc, so any physical activity that involves quick, short bursts of energy makes heavy use of the ATP Pc system. When the 10 seconds worth of Pc is used up, muscles start relying on the second anaerobic energy system for the bulk of their energy. This second anaerobic energy system is known as the lactic acid system. It works by synthesizing new ATP molecules from glycogen, which is the stored form of sugar in our bodies. The reaction is known as glycolysis, and because it doesn't involve oxygen, it's called anaerobic glycolysis. Through a complex series of reactions, glycogen breaks down into ATP and lactic acid. This anaerobic glycolysis occurs when muscles are working above their lactate threshold, something we'll look at in more detail later in the program. As lactic acid builds up in our muscles, they begin to hurt and feel stiff, and this serves as a signal that our muscles are wanting a rest. Anaerobic glycolysis is the basis of the lactic acid energy system. During high-intensity exercise, it takes about 10 seconds to really kick in and lasts about another 20 seconds or so before the third system starts to play the most important part in providing muscles with the energy they need.
So we'll look at the aerobic part in just a second here, but that's the anaerobic parts of your metabolism, right? The anaerobic without oxygen parts are ATP Pc system and the lactic acids, the glycolysis, right? Both of those take place in like outside the mitochondria, right? So if we look at an animal cell, right, these both take place. The other thing they want you to know is where this is happening. It's happening in the fluid of your cells. Okay, so it's happening in this empty space here, which is not so empty. It's fluid, right? There's this stuff called cytosol or cytoplasm. You'll hear it referred to as sometimes, which is all the liquid stuff inside of every one of your cells. All your cells are very swampy. Then once we have sufficient levels of like byproduct created, and once we start driving oxygen into the cell, the energy production will move across the membrane of this little, almost like bacteria looking thing here called your mitochondria. And the mitochondria is where we're going to produce energy for the oxidative part of the metabolism. And the oxidative part of your metabolism, like I said earlier, is very, very complicated, right? It is so complicated, it has 3 parts to it. And one of them we haven't even really talked about because it's not really a thing. But you do have aerobic glycolysis. And that's like, wait. We just said glycolysis was anaerobic. It is, but sometimes there's some finishing glycolysis that will happen just on the inside of your mitochondria, which is an oxygen bubble rich environment, right? So aerobic glycolysis is glycolysis that's happening just on the inside. We don't have to worry about it because honestly, they're the same thing. Then you've got the Krebs cycle, and the Krebs cycle is where, again, you use that lactic acid that we produced in the lactic acid system or glycolysis. We use all that to produce a little bit more ATP and that NAD and FAD, the NAD and FAD. And then NAD and FAD will finally go through the electron transport chain, which will produce 36 molecules of ATP. But it took forever to get to this process. We have to wait for glycolysis to finish. We have to wait for the Krebs cycle to finish. Then we can do the electron transport chain. So this produces a lot of ATP, but it produces it very, 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 very slowly. So that's why it's very good for sustained energy, right? You have this other stuff that's kind of going on in the background. Glycolysis doesn't stop when you start, doing long duration activity. It's still happening in the background. It's just not providing you with much energy that's being used. Its energy is used to basically keep these other 2 systems running. This is where you're getting the energy for the activity, right? So it's producing ATP at kind of a slow rate, but it is producing a whole bunch of it. And that's what keeps you, this is like all the stuff that's keeping you upright right now. And then fat can be used here as well through like that beta oxidation, and it basically just skips straight to this Krebs cycle electron transport chain section there. So here's the other half of the video where we're going to go through your aerobic system, right?
The aerobic energy system works by supplying oxygen to the muscles. This is the most complex of the 3 energy systems and requires the heart, lungs, and whole circulatory system to work. After about 30 seconds of intense physical activity, the aerobic energy system becomes the main source of energy. It is at this point that large quantities of oxygen carried by the blood becomes available to the muscles. The presence of available oxygen to the muscles allows a process known as aerobic glycolysis to take place. This process uses the large stores of glycogen in the body, which is synthesized into ATP. Water and carbon dioxide are byproducts, which the muscle cells expel via the blood. This expulsion of the waste products prevents muscles from becoming fatigued in a short period of time. With the heart and lungs working harder to move greater volumes of oxygenated blood around the body, aerobic energy allows the muscles to keep on working and working. As well as using glycogen as the basis for ATP synthesis, the aerobic energy system can also use the body's fat. However, this requires large amounts of oxygen, So for moderate to intense physical activity, glycogen is the preferred source of ATP. But after about 2 hours of continuous aerobic activity, glycogen is all used up and fat takes over as the source of ATP synthesis. Marathon runners say they can detect when this occurs in the body and refer to reaching that point as hitting the wall. Because greater amounts of oxygen are used in breaking down fat, less is available to working muscles, and athletes must rest or slow down. In extreme events, such as famine, body fat can also become totally used up, and protein then becomes the source of ATP synthesis. The aerobic energy system requires heart, lungs, and circulatory system to provide oxygen to muscles. Aerobic glycolysis synthesizes ATP from glycogen. Water and CO2 are byproducts, which leave the cells via blood flow. The aerobic system becomes the dominant energy source after about 30 seconds of intense activity and can sustain around 2 hours of continuous aerobic activity. After this point, fat becomes the main source of ATP synthesis.
So, those are your energy systems, right? Now, let's go ahead and take a look at actually like applying this in a practical setting, right? So we've already kind of talked a little bit about it, right? We talked about like, choosing your repetitions specifically, right? But one of the cool things is intensity and duration of exercise. We know those are inversely related, right? You can't do high intensity for long duration. Your 1 rep max can be done for 1 rep, like if you can do it for more than that, it's not your 1 rep max, right? And so there's this inverse relationship. As intensity climbs, duration will drop. As duration climbs, intensity will drop. And this is why like a 100-meter dash is extremely intense, whereas like a marathon is extremely non-intense, at least in our vocabulary, right? When we're talking about intensity, we're talking about your maximum effort per repetition. I'm not saying a marathon isn't hard. I would argue it's honestly harder than a 100-meter dash, mentally and overall physically, and repairing the body wise afterwards. But it is less intense. So we got to make sure that we keep those terms kind of specifically meaning what we want them to mean in our jobs. So your body position also plays like a role here. So when we're looking at like how much energy is being used during exercise, body position plays like a little bit of a role. So imagine like if you're doing just bicep curls, you're not burning very much energy, right? Even if you are working really, really hard, maybe it's super heavy, right? Well, you're just kind of sitting there, using one little tiny muscle. So if we want to like increase the amount of energy that we are expending during our workouts, well, then we want to make sure that we do not have our clients laying down. We want to have them at least sitting upright. And then beyond that, we want to have them hopefully standing. So laying down burns less energy than sitting. Sitting burns less energy than standing, because it's dependent on how many muscles you are recruiting. So if I had a weight loss client, right, and I can choose between like a bench press, which would be a position where they are maybe laying down, and then I can choose between a chest press machine, which is where they are sitting upright, in something like this, or I can choose between a standing cable chest press, where now they're up on their feet while they're doing it. This may be my best option because this is going to burn the most amount of energy. Now I'm trying to develop strength in my chest. Well, we'll go back to the bench press as our best example because it's very stable, it's very heavy, right? But again, like we've got different goals depending on like what it is our client wants to achieve, and we need to think about those when we're picking our exercises. Now, luckily, NASM's done that for you. That's why the OPT model exists, but it's definitely something we should still consider. And then there's a really fun concept that I want to talk about, which is called Epoc. So Epoc stands for excess post-exercise oxygen consumption, EPOC, and it's an elevated oxygen consumption after strenuous exercise. So after yesterday's cardio session, probably noticed you were a little warm, probably noticed that your heart rate stayed elevated a little bit, even after you were done exercising. Well, that is your body converting all the lactic acid that you generated during your workout. Now that you're done, like, and you're chilling and you're relaxing, you're not working hard anymore. All of that like lactic acid that you did produce like during your workout, it's still laying around. So your body's going to try to get rid of it. So it's going to keep bringing in lots of extra oxygen in order to like convert that lactic acid into energy, which is also why like after exercise, sometimes you feel like you have more energy than when you first went to the gym. And that's because all the lactic acid you generated is being converted into, lots and lots and lots of energy. So Epoc is this elevated calorie burn that happens after strenuous exercise. It's your time taking like while you're catching your breath. Now, generally, we think of like catching our breath as like, you kind of catch it after, 30, 60 seconds, and so is the big elevated calorie burn done at that point? Well, not necessarily. Sometimes we've seen it last up to 72 hours in some people. So your body will continue to burn an elevated number of calories in response to any intense exercise you do. So the more sprinting, the more max effort you do, the more likely you are to develop Epoc. Low intensity, long duration exercise doesn't have the same effect. Low intensity, long duration exercise builds way less Epoc because you're recruiting less muscle fibers to get the job done. So marathoners will have less Epoc than people who are doing like HIIT sprint interval training. In fact, they've done studies that we're going to talk about at the end of this module, where they took two groups of people and they had them burn the same number of calories. Let's say it's 500. So two groups of people both burned 500 calories every single day through exercise. And then they were all given like the same diet and stuff as well. And then what ended up happening is the group that, and they were divided into two groups. One group burned 500 calories at a steady state. They would hit a number on a treadmill and they would just go at that pace until they hit 500. The other group would take their intensity up and then they would recover and they would take it up and they would recover. They were doing HIIT interval training or high intensity interval training. And that group that did the HIIT training lost nearly twice as much weight as the first group. And most of that weight came from body fat rather than just body weight. So what the heck happened there? Why do they burn so much energy? Well, they developed more Epoc. They burned more calories once they were leaving the gym. And they burned calories that stayed elevated. They boosted their metabolism for, like I said, up to 72 hours. Although it should be stated at 72 hours, it's very, very little. Honestly, think of it for a couple hours. But that's where we have to look at something called your respiratory quotient as well. So going back to what we talked about earlier, right? Remember the respiratory exchange ratio or respiratory quotient. Right, we looked at this earlier. It's moving between a blend of burning carbohydrates for fuel versus burning fat for fuel. So the Epoc group, they were doing high intensity interval training. So they were probably getting their RER up to somewhere around 1.0 for maybe a few seconds. And then they were recovering, they weren't like fully going into like sleep, right? They weren't resting entirely, but they were probably like bringing it down to like maybe an RER of like 0.88, where suddenly like, okay, or maybe, probably close to like 0.85, which is basically 0.85 is the middle number. So they would recover in the fat burning zone, and then they would like work really hard in the carb burning zone. They would use the carbs to basically give them a big calorie boost, and then they would utilize that calorie boost when they were burning more fat for fuel. So respiratory quotient, at rest, we are in an RQ of 0.7. Fat is your primary fuel source. When we're at a full sprint, we're at an RQ of 1.0. Carbs are the primary fuel source. So we're always in a blend between those two. So the reason interval training works so well is because you get a big calorie boost from doing the interval training where you're in the carb burning zone. And then you recover in the fat burning zone. And it lasts for a couple hours, which means at some point you're going to go home, you're going to sit on the couch, maybe watch a new episode of Loki on Disney or whatever. Or maybe you're going to end up watching, or maybe you're going to go to bed, right? And you are burning extra calories. And when you're in bed, you're at an RQ of 0.7. So all of your calories are coming from fat, but now you're burning more calories than you would have thanks to the workout you did earlier in the day. And that's why we love interval training so much. It's been shown to be so effective. So summarizing everything up, bioenergetics is how we are studying turning proteins, fats, and carbs into energy. Metabolism is all of the chemical reactions that are taking place. We talked about a lot of chemical reactions today. Proteins, fats, and carbs are those fuel sources. ATP is the molecule we're trying to generate. And your respiratory quotient determines whether you are burning fat or carbohydrates, or hopefully not protein as a fuel source. And that's about it, guys. Questions, comments, concerns. How's everybody feeling? Thomas, Bay, Cody, how you guys doing? Got the thumbs up from Bay. Doing good, guys?
Yeah, it's good. Thank you.
All right. Love it. All right. Well, ladies and gents, I will see you guys on Tuesday. We got the 4th of July weekend. So Monday, there is no school. And I will see you Tuesday morning, bright and early.